The next major topic we covered was integration. So in preparation for the final exam, let's do a couple practice integration problems. The first problem we're going to do is the integral of 15x to the fifth plus 3 over x minus 4e to the x plus 5 over x squared plus the cube root of x dx, just to make sure we remember all those integral rules. When we're taking an integral, we don't like to have fractions and radicals, except for over x. That one's allowed because that one has an easy antiderivative that we know. But the other ones I'm going to rewrite. So we have 15x to the fifth plus 3 over x minus 4e to the x plus 5. We're going to write that x squared as x to the negative 2. And that cube root of x is a 1/3 power. Now we can go term by term, and we can take the antiderivatives. First thing we're going to do is we're going to increase the exponent by 1 to make it 6, giving us 15/6, which I can reduce to 5 over 2, plus 3, and the antiderivative of 1 over x is the natural log of x, minus 4, the antiderivative of e to the x is just e to the x. Then we're going to increase the exponent by 1 to get x to the negative 1 and divide by that new exponent, giving me a negative 5. Plus, we're going to increase this exponent by 1, giving me 4/3, and multiply by the reciprocal, which gives me 3/4. And of course, every antiderivative is going to have that plus c on the end. That's the general formulas for antiderivatives and integration. Let's see if we can use some of our integration tricks, starting with the integral of x to the 7th e to the x to the 8th dx. What you might notice is the derivative of x to the 8 is almost sitting in the problem. So we're going to use that and use a u substitution, where u is equal to that x to the 8th. And then the du is going to be 8x to the 7th dx. Well, we need to get an 8 in there, so we'll multiply and divide by 8. Because it's a constant, we can do that. And the 8x to the 7th dx can all become the du. So we have 1/8 of the integral of e to the, all that stuff became u, and the rest of it became a du. E to the u's antiderivative is e to the u, so we have 1/8 e to the u plus our constant. And then we just have to replace the u with the x to the 8th that it represents. And we get 1/8 e x to the 8th plus c. We've got our solution. How about we try this integral? Let's do the integral of dx over x plus 3 to the 5th. This would be really nice if it was not x plus 3 to the 5th, but just a u to the 5th. So let's see if we can make u equal to x plus 3. Sure enough, that means the du, the derivative of x plus 3, is just dx, which is really nice. Then our integral is going to become the integral of the dx becoming a du over the x plus 3 becomes a u, and then it's still to the 5th power. And we can rewrite that as the integral of u to the negative 5th du, so that we can just use our integration formula, where we increase the exponent by 1 and divide by the new exponent. Don't forget the plus c, and then go back to the original u of x plus 3. So we have negative 1/4 x plus 3 to the negative 4 plus c for our final solution. Sometimes the problems, though, got a little more complicated, and we weren't able to make a u substitution. Let's try the integral of x to the 4th times the natural log of x dx. Here, since we have a product and u substitution doesn't work, let's try integration by parts, where we use that LAY acronym to help us decide what comes first. Logs come first, so u is equal to the natural log of x. And the dv is the rest of it, which is x to the 4th dx. Then du is going to be the derivative of natural log of x, which is 1 over x dx. v is the antiderivative of x to the 4th, which is x to the 5th, times 1/5. Now we're ready to take the antiderivative. We'll do u times v, which is 1/5 x to the 5th times the natural log of x, minus the integral of v du combined together. And I'm going to kind of change the order here. The 1/5, I'm going to move that out front because it's a constant. And then I've got 1 over x times x to the 5th dx, which is really nice because that x in the denominator reduces out with one of the numerators. So we have 1/5 x to the 5th natural log of x minus 1/5 x to the 4th dx integrated. So that final result then, after integrating, gives us 1/5 x to the 5th natural log of x minus, we'll increase the exponent by 1 and divide by the new exponent. So we have 1 over 25 x to the 5th. And of course, we never forget the plus c. And we've got our solution. One last thing I want to take a look at before we step away is making sure we know how to do definite integrals, like the integral from 1 to 2 of 8x to the 3rd minus 4x plus 2 dx. The integration is still much the same. We'll integrate by increasing the exponent by 1 and dividing by the new exponent, minus increasing the exponent by 1 and dividing by the new exponent, plus 2x. We don't need the plus c because we're going to integrate from 1 to 2, and those c's are going to subtract out. So now we can take the top number and plug it in. 2 times 2 to the 4th minus 2 times 2 squared plus 2 times 2. And then we'll subtract, plugging in the bottom number. Making sure as we do, we subtract all the way through, changing all the signs. So I have negative 2 times 1 to the 4th plus, because we're subtracting a negative, 2 times 1 squared minus, because I'm subtracting a positive, 2 times 1. Working that out, 2 to the 4th is 16 times 2 is 32. 2 squared is 4 times 2 is 8. 2 times 2 is 4. Minus 2 plus 2 minus 2. When you put all that together, you should get 26 for the total area under that curve. Make sure you're very comfortable with the integration tricks, with u substitution, with integration by parts, and also with these definite integrals, plugging in the limits of integration. We have one last video in our review, and that's about the applications of integrations, and that's coming up next.